All right, hi everybody. Welcome back. So today we'll be covering. This is a bit of a follow-up on our previous lesson where we looked at some intro Python. We familiarized ourselves with the Jupyter Lab environment, with kind of this idea of writing up code cells and executing them one at a time. But last time, what we did really was look at some basic Python in terms of basic object types, or containers for data, if you will. We talked briefly about how to make some custom functions. But today, what we're going to do is take it a bit more of an intermediate level. And we're going to learn about how to do some data analysis in Python, building on what we've already learned. So on top of that, we're also going to be covering a bit of, well, not super in depth, but just enough to kind of get up to speed with the rest of the lesson, some of what are known as classes, in particular, kind of the utility they offer within Python, why they're an incredibly useful feature of Python, and hey, come on in. And even briefly how we could write our own if we so choose. So I'm hoping everybody has the Jupyter Lab environment opened. If anyone needs a hand with that, just wave over at James and he can walk over and help you out. I'm going to be covering the first half of this lesson. And then after that, James will be teaching the second half. So I'm just going to wait a quick second. We've got a few people coming in, wait for them to set up before I launch full steam ahead. All good. Just get Anaconda open and give me a thumbs up when you're ready. So when you're opening your Jupyter Lab instance, make sure to do so via Anaconda, because we're actually going to be using a few packages or libraries today that Anaconda already has pre-installed for you, which saves us some time. Just a functioning version will do. Yeah.
And the kernel is Python 3 or?
Python 3, yeah. And if there's an option between Python 3 and Python 3 Conda root, pick the Conda root one. That's fine. We're going to be typing everything as we go. All right, people coming in now, are you pretty much all set to go? Sweet. Great. So to begin with, this here, as a quick reminder, is Jupyter Lab. This is considered a code cell. We can write in standard Python code in here, such as x equals 2 or print x, and then execute all the code within a code cell with the Shift-Enter shortcut, or by the play button up here, whichever you may prefer. Another quick reminder is that if you'd like to take notes for yourself, you can actually change one of these cells using this drop-down over here to Markdown. And once you do that, this cell becomes a text cell, and then you can write any form of text in it that you'd like. This is a Markdown cell. Using the Shift-Enter shortcut or the play button on this again will make it render as standard text. And this is a great way to kind of organize your notebook, keep some notes to yourself, and just kind of intersperse your code with whatever notes you might want to do and want to add. So again, we're assuming you kind of have some familiarity with variables, lists, functions. But if anything is completely unclear to you, feel free to interject and maybe ask, and I can give a brief explanation of what might be going on somewhere. Alternatively, flag James as well if you'd like. So last time we talked about various various object types, such as so this over here is an integer. We might remember. We also learned about strings, so storing text information. So for instance, my string equals to, I don't know, NASA. And these are all various ways that Python can encode information, all within this sort of consistent syntax. But it also might intuitively follow that certain types of objects might have certain specific operations associated with them. So for instance, if we were to have a list, so we can create a list using the square brackets we learned about last time. So let's create a list called mylist equals using square brackets, 1, comma, let's say 5, comma 1, comma 1, comma 3. So this is a list containing 5 integers, and a natural operation we might have with this list, or perhaps one containing more interesting data, is how many times does a given element show up in there? So to be more specific, how many instances of the value 1 do we have in this list? So this is the sort of operation we wouldn't really be thinking about in terms of a single value, right? It's more unique to the way a list is structured. So with that in mind, Python actually offers these things known as methods and attributes that are specific to a given object type, allowing you to perform certain operations on them. So actually, let's format this a bit nicer here. Sorry, I should have started with that. I'm going to format this as methods and attributes. If you had a hash over here, it'll format it as a header, as a bit of header text. We can add 2 hashes to make it slightly smaller. So one way we could perform that operation of counting how many ones are in there is writing some kind of convoluted looping structure and going through these one at a time and keeping count. But alternatively, we could use a certain list method. So there's one helpful list method for this operation known as count. And the way we would actually execute this is a bit different from what we might have seen last time. So I'm going to write this out. Bear with me for a second. We would write my list first, then dot count. Notice this actually gets highlighted in a slightly different color as well. Then we add a pair of parentheses, and we write in the element that we're interested in counting, which in this case is the value 1. Once we run this, what Python will actually do is count how many times 1 occurs within this list and return that count to us. So let's take a second to really kind of internalize what's going on with the syntax here. This is a method. It's essentially like any other function, like print, for instance, which we have up here, in that it takes in some sort of object, perhaps other inputs or arguments, and then returns something. The difference here is that when you're working with a method specifically, it's kind of attached to an object. In a sense, you can think of the first argument, the first input it receives, is the object itself. So method is a function attached to an object that acts on the object. That's why we use this sort of syntax. We use a dot to denote that we're going to start writing out a method. And then some of them take inputs, such as this one, and some of them don't take arguments. It depends on the method. Alternatively, if we look back at our string over here, a string operation might be, for instance, what if we wanted to convert all these letters to uppercase? In that case, strings have a helpful method called upper. So I'm just going to write out my string dot upper. And then just an empty pair of parentheses, because it doesn't take in any further arguments. If you were to run this, this would actually return NASA in all uppercase. It would modify that string and return it to you. Now, an important thing to mention about methods is they are sometimes a bit inconsistent in their behavior, in that these methods over here, they return something completely new, as in, so my string.upper has returned a new string called NASA. It has not, and we can check this, affected the original string. Print my string, it's still lowercase. Some methods, however, will affect their given object types in place, and that's just something to keep in mind. It's a bit of a case-by-case basis. So the idea that upper is kind of unique to just strings kind of makes intuitive sense. That's not an operation we would perform on a list. It's not an operation we would perform on a number. So this is a really useful way of grouping related functions, related kind of pieces of information together. And in fact, Python allows you to create your own custom. You could think of them as object types, but these are known as classes. So classes allow these related objects to be logically grouped together, then used throughout your programs, throughout your scripts. And this might be a bit of a jump, especially like if you haven't necessarily programmed in this sort of object-oriented fashion before. But let's walk through a bit of a brief example, and hopefully it starts to come together a little bit. So far we've been dealing with these base Python classes, lists and strings. But let's create our own. Let's say we wanted to create a unique class specifically to store information about vehicles, let's say. So we can do that. I'm going to actually make this a markdown cell and add a new header, classes. And then just add some blank cells down here. So to create a class, we have to use a special keyword, which perhaps unsurprisingly is the word class. You'll notice this also highlights differently. And let's say we just wanted to call our class vehicle with a capital V. So we can do just that by writing out class vehicle and then following that with colon. Following that, just like with our functions, we can add a bit of documentation over here. So we can do so by adding in 3 quotation marks, 1, 2, 3. You'll notice that immediately doubles up. And in the middle of that, we can write something describing this class, such as basic class describing vehicle. So what are some attributes a vehicle might have? I mean, we know that most vehicles have 4 wheels, so that's one. So we could create a variable associated with instances of this vehicle class called num wheels and set that equal to 4 by default because motorcycles don't exist. Let's say, however, the color is less set in stone, so we'll kind of initialize this variable. That's one way to think of it, I suppose, called color, but we'll just keep it an empty string for now. And why that is will make more sense in a second. These here are 2 attributes we've defined. Up here, we dealt with some methods. Methods are functions associated with an object type. Attributes are pieces of information that are associated with a given object. And we'll look at how to kind of call upon attributes and change them in a second. However, if you wanted to actually write a custom method, so again, a function specifically associated with this, we would actually start on our traditional kind of function syntax. So using the def keyword, just like we would with any sort of a regular function, we could create a function called description. Now this is key, however. We might remember from last time that our function arguments are usually some sort of placeholder variable like input or num1. When it comes to class methods, the first argument is self. And what self means is that is basically when this method is called upon, its first argument is the object itself. So it's this kind of, it's a bit hard to explain. But just keep in mind that when you're writing class methods, the self thing is important because that's what this function is acting on. Again, it's a bit of a jump from what we've talked about last time. If it's not making immediate sense, that's fine. But hopefully when we're on the other side of this, once we've actually made this class, it'll make a bit more sense. So as with our previous function, we could add a colon here, hit our previous functions, hit enter. You'll notice an indent shows up. And we could have this description function just print out a quick description of our vehicle. So we'll write out print, open a string over here, and say this vehicle is so okay, here we're at a bit of a conundrum. How do we make it print out kind of intelligently what's going on over here? How do we make it print out how many wheels it has, what its color is, while within the string? And I'm just going to quickly introduce something known as string formatting. This is a way of substituting in variables into strings. So let's just write this out first and then break it down. So I'm going to add a pair of curly braces here, write 0 within them, and then after that, write and has curly braces again, 1, close curly braces, wheels. Then at the end of your string over here, right after the quote, but before the parenthesis, add dot format. So this actually is another example of a string method. Dot format, then open a pair of parentheses and write self.color, comma, self.num wheels. I'll give you guys a second to write all this down. It's a lot to take in. All right, so the way string formatting works is essentially whatever's in these curly braces, the 0 and 1 indicate the order in which basically these things get substituted into the string. So when we actually print this out, Python will take whatever's over here, so that's going to be the color of this object, and substitute it in here. And then same goes for the number of wheels, which it'll substitute in here. So let's actually just run this and see what it looks like from the other side, instead of just describing what we think it's going to look like. Before we do that, though, just a quick reminder that you can use the help function on pretty much anything, but including this vehicle object we've just made. So bear in mind that you have to run this cell up here. If you were to type in help vehicle with a capital V, it'll actually print out pretty much all we just did here. So that's our description, basic class describing a vehicle. the methods defined here. So description was our only method. And if you scroll further down, the other attributes are color and num wheels. So that's all well and good, but how do we actually access these? So first, let's actually create an instance of the vehicle class. We'll create an object called sedan. Sedan? I forgot how to pronounce that. Vehicle with a capital V. And we'll just write an empty pair of parentheses here. Once you run this, we've created an instance of the vehicle class. This is the same way you can think of there's a template for the list class, and then whenever we create a new list, it's based off of that. So sedan is just one instance of vehicle. And we can check how many wheels our sedan has. So we'd go print sedan dot num wheels. Now don't add parentheses at the end here. You'll see it prints out 4. Now, the reason we didn't actually add parentheses over here is because parentheses are specifically for methods. Remember that methods can be thought of as functions associated with that object, right? Attributes, however, are just pieces of information. The parentheses at the end are not really needed because this isn't actually doing anything per se. It's just returning a piece of information associated with this object. So this is an example of an attribute. So calling an attribute. Method, on the other hand, well, actually, we'll get to that. Let's, sorry, I jumped ahead. So remember that I left the color blank. The cool thing is we could actually reassign a certain color to our sedan object. So we could say sedan dot color equals, let's say, black, because we're slick like that. And then just print out what the sedan's color is. Now our sedan actually has a color. Initially, it didn't have any color at all, but we could actually assign this string containing the word black to that attribute, and now it is part of this instance of the vehicle class. Finally, now that we've got a color and a number of wheels, we could run our method, sedan.description. This time we need parentheses because this is a method, remember. So calling method. And now we can see our string formatting at work. So let's take a quick second to scroll back up. Over here it says this vehicle is black and has 4 wheels. What Python has done is there it's subbed in black, which was the color that we assigned to our sedan, and there it's subbed in the number of wheels, which we didn't modify, and so is left as 4. So it's subbed in color over here, and then it substituted the number of wheels into here.
Do you have to start with 0 there?
Yes. If you're doing them positionally. There's other ways to string format as well, but if you're just writing out what you want to substitute in order, then yes.
Another reason is that you could use the 0 at multiple points throughout the string, and it's always going to be the first thing in the parentheses. So like if after the 1 you put another curly braces with 0, it's going to substitute color. Because
again,
color is the 0th thing after.
But you can start with 1, and, for example, instead of 0, 1, and then 2.
Yeah, you can, but then it would put wheels and then color.
So it's worth remembering then Python indexing starts at 0, right?
Okay.
Yeah. So 1 would be this, and then there wouldn't actually be any index 2.
Okay.
So this here is like the basic syntax of a class. Classes are relatively advanced. Again, I've said this already, but they will take a bit of time to wrap your head around, and actually might be a while before you find yourself writing a class of your own, as useful as they are. However, one really useful thing about this kind of object-oriented programming framework is it makes Python extremely extensible. You can create an object type for virtually anything. And that's going to form the basis for what we're actually going to look at for the remainder of this lesson. So what a whole host of programmers around the world have done is created various functions, like custom functions and custom classes for all sorts of specific operations, perhaps with applications and stuff like genomics, neuroscience, and so on. And once they do so, they actually package these together into code bases known as libraries, also informally known as like packages or modules. And these are just freely available for pretty much anyone in the world to install on their own computers and use. So data analysis in Python is essentially based around these modules. Although you can try to do that sort of thing in base Python, it's arguably way easier to use these really specialized and useful object types people have made. And the great thing about using Anaconda, which all of you guys have installed, is that all of these are already installed for you. So Anaconda comes pre-installed with the most common libraries for data analysis in Python. So we're going to start here. I'm going to change the store markdown cell with the NumPy module. Or library or package, just pick a word and stick with it. So NumPy is short for numerical Python, and it's a Python library for quick and efficient mathematical operations. And however, if you actually want to use it, we would have to first import it into our workspace. If you've programmed before in something like R, this operation is likely familiar to you. The difference is in Python, the keyword we use is import. So just write out import, and then you'd write out NumPy. Now don't run this just yet. The cool thing about importing libraries in Python is that you can actually give them like abbreviated names or aliases while you're importing them. So at the end of this, we're going to add as NP. And this will be important in a second. What this basically means is if we'll want to refer to NumPy in our code, we can just write NP, which it's kind of convention. The community seems to do it, and it's pretty handy to do. So once you run that, it shouldn't output anything, but it should run just quietly. And now we've imported all sorts of NumPy functions into our workspace, and we can start to use them. So NumPy is kind of the backbone for, I would wager, most data analysis libraries in Python. And one of the key object types it offers for why that is known as the array. So the arrays allow for incredibly computationally efficient, first of all, operations, but in addition to that, they're vectorized. So let's actually create one, play around with it, and hopefully we can see some of the advantages that it offers. So we can create an array, and we'll call it myArray equals. And this time, since we're using the array object within NumPy, we have to start by writing np.array. This is kind of similar to the methods and attributes syntax we saw, right? Object.thing. So np.array tells Python to look for the array object within np, or NumPy. To create an array, we open a pair of parentheses, as we would for any function, but it takes in actually a list as its input argument. So within here, let's create a list. Let's add in a bunch of numbers, say 1, 7, 12, 6. After we've done that, just print out my array. All right, and it looks like a list so far, right? It's got square brackets, it's just got numbers in it. Is there a question?
Yes.
Yeah, what's up?
So when you load the NumPy, it's a library, right?
Yes.
So do you have to specify it each time you use it then?
If you're using anything that's within the package, so whether a function or a class, then you have to preface that with NP. Yeah.
Okay, it's not loaded like.
No. So there's syntactical ways around it. You can import it in a way that you would just write array, but it's recommended to not do that. Doing this makes everything very explicit. If you're coming from an R background, it's the equivalent of writing, for instance, np : array to specify that that's the package and that's the function from it. But in Python's convention to actually always do it this way, to be very explicit about where a given function or class might be coming from.
Okay.
So arrays look like lists so far, and in fact, they can be indexed and sliced like lists. So like before, we could use our square bracket notation, so my array square brackets, let's say 2, to get the item at index 2, which is the third one. In this case, that's 12. Similarly, we could slice as we did with lists. So my array square brackets, and we could write 1:3, which pulls out the elements at indices 1 and 2. So notice it's actually formatted a little differently. It says array and then what's actually contained within. However, the first kind of big difference you'll notice is that, I mentioned this already, but operations in arrays are vectorized while operations on lists are not. And so in this sense, arrays are a lot like vectors, vectors in R even. So if I were to say my array times 2, actually wrap this all in a print function. But underneath that, just for comparison's sake, let's copy down the list we have in here. Just copy to clipboard, print, and then write out that same list times 2, and then run this. So Python lists are pretty funky that way. If you multiply them, they just kind of double up on themselves, which is very impractical if you're trying to do any sort of vectorized operations. Whereas NumPy arrays will understand what you're trying to do here, and in the vectorized fashion, in this case, multiply every element by 2. So there are a few quirks with NumPy arrays. I'm just going to write it here. Arrays have a fixed type. So again, much like R vectors, every element in an array has to have the same type. That means you can't even have integers and floats in the same array. So if I did try to change, let's say, the element at index 1 from, what's that, 7 to like 7.15, and then print it out in my array, NumPy would have none of it. It'd be like, nah, we're sticking with the integer 7 over here. And I believe it rounds to the nearest integer, assuming this is an array of integers, of course. If, however, our initial array was just consisted of floats, then it wouldn't mind this at all. It's the main thing that matters to NumPy is that its elements are all the consistent type. So just a bit more NumPy, and then we'll move on to data analysis. Sure.
If you wanted to be able to figure 7.15 in that array and have them all floats,
yes.
How would you?
That's a good question. I don't actually remember off the top of my head.
Array might have like a 2 float or like a change D type.
Yeah, that's likely. And this is actually something I wanted to mention earlier. If you type in an object name, add a dot, and then hit tab in Jupyter, it actually lists out all the methods and attributes available to you.
Type.
What's that?
As type, the method as type.
Oh.
You might be able to just do as type float.
Neat. Yeah. All right, now we know. But yeah, that's actually super useful because there are very few methods I remember off the top of my head. So if you type in an object name, dot, tab, you could go through these and pick them out. And then, of course, use the help function on them to figure out what you might, what each method might do.
I have a basic question, but
Sure.
I don't know very well what is float.
Float it's a floating point number. In R, it's what we'd consider numeric instead of integer. It's basically a number with decimal point precision, whereas an integer is always a whole number.
Okay.
So a Python like R, although I guess it's less noticeable in R, Python treats them differently and isn't always nice about like changing one to the other implicitly. So it's worth keeping them separate. Okay, so here are a few quick convenience functions. Rarely will you want to type out arrays manually, especially if you're writing out more than, let's say, 4 numbers. So a few convenience functions for quickly making arrays. So the first is arange, and I'll just print out each of these as I write them. Arange 1, 10. This will just have an array with values 1 to 9. Because remember, in Python, most ranges are end exclusive. So this will just be values 1 to 9. And print this out just to make sure of that. Another common sort of operation to make an array is to define a range, let's say from 0 to 10, and then split that into a number of values. So let's say you want 5 evenly spaced values between 0 and 10. So for that, we have the function linspace, which you would write 0, 10, 5. And that would be evenly spaced values, from 0 to 10. Or rather 5 evenly spaced values, because obviously you can modify how many there are. And here we have 0 to 10 partitioned into 5 values. So that might be a handy way you find yourself making arrays. Finally, this is a useful one if you want to kind of initialize an array and then later just plop numbers into it. np.zeros, without the E, I believe. And then you just give it a number, let's say 8. This will create an array of 8 zeros, or however many you want. Effectively like an empty array for you to place values into. I'll give everyone a second to write that down. So one more quick thing is that arrays can actually be two-dimensional. So for those in the room who do any sort of linear algebra and or fiddle with MATLAB, you might be happy to hear this. So you could actually create, let's call this my matrix, np.array, open parentheses. Now this is a bit funky, but you have to give it a list of lists. So we're gonna have an open set of square brackets, but I'm just gonna hit enter right away to split them between two lines. So there's our opening brace, and there's our closing one, or opening square bracket. And then within here, you could write 3 lists. So, or however many you want. 1, 2, 3, comma, 4, 5, 6, comma, 7, 8, 9. And we don't need a comma at the last one because that's the final one. I'm just splitting these across different lines for readability. And then if you're to print out my matrix over here, NumPy kind of respects that you're trying to do a two-dimensional array and it actually preserves that structure. So hopefully at this point, if you were ever thinking about doing numerical operations with lists, that's just kind of out the window. So in the interest of time, I'm not going to go too much into slicing and indexing here. Essentially, they're kind of, you can use square brackets again to pull out chunks of this. I'll just cover some of the very basic ones. So my matrix, if you want a given value, you would use the sort of classic row column coordinate system. So 1, 2 would give you the value at row 1, which is the second one because Python indexing, and then column 2, which is the third one because Python indexing. So that should be 6. If, however, you just want my matrix, if you just want a row and like all for across all columns, you would just sub out either the value that you're not specifying with a colon. So 1, colon will return row 1 for all columns, and analogously, if you were to replace print my matrix colon 2, so that's all rows for column at index 2. So that's 3, 6, 9. So, but I'm not going to dwell on this too much longer. And just to wrap up, NumPy has some really helpful functions to generate random values. This is something I find useful, especially when like trying to program some sort of random draw or something along those lines. So the first one is for drawing a value between 0 and 1. And we can actually just do this 10 times for fun. So if you might remember for loops from last time. For I in range 0 to 10, so that should be 10 iterations, we'll have it print I, comma, and here's the kind of magic function in question, np.random. But the final one, add this pair of parentheses. Now the reason we have 2 randoms here is because NumPy actually has a sub-module called random. And within that, there's a function called random. So that's why we've got 2 of those over there. But if you were to run this, it'll very quickly do 10 draws of values between 0 and 1, which is handy for all sorts of reasons. Finally, to wrap up, you could also draw several integers between a range.
What are the values?
They just are by default. Yeah, but if you want to specify a range of integers to draw from, that's what we're going to look at next. The random module is actually much larger than this, but these are just 2 representative functions. So for I in range 0 to 10, print I, so the iteration we're on, and this time we'll write np.random.randint. Then 1, let's say draw a value between 1 and 10. In fact, you could even give it a third argument for how many you want to draw at a time. So let's say draw 3 values at a time. Once you run this, for every iteration, it'll draw 3 values between 1 and 10. So it's extensible in that way as well. So for instance, I've used the random module for if I'm like going through a large file and I just want to keep 30% of it at random, you just do an if statement of if np.random.random is less than 0.3, then draw the next data point or whatever. Okay, this is just the tip of the iceberg with NumPy. There's so much to this package that even I have yet to discover, but if you ever find yourself doing numerical kind of anything matrix or vector related or any sort of numerical work at all, NumPy is your best bet. Has been the best bet of many other developers as well. To the point where, like I said this earlier, many data analysis libraries are built on NumPy. One of these libraries just so happens to be called Pandas. Has nothing to do with the animals, unfortunately. But it's a means of actually working with data frame objects within Python. And for that, I'm going to hand it over to James, who will take it from here.
All right. Let me just... Cool. Does anybody have any questions before we go on to Pandas?
Sorry.
Just to like recapitulate a little bit, like the idea of sort of instantiating objects using classes. So like we created arrays, like instances of the array class from the NumPy module. And then we used various methods from the array class to like do things like, well, actually we didn't use any, did we? Count elements and stuff, but that's okay. But I'm going to create a markdown cell as we move on to the next part of the lesson. So the pandas module, and create a bunch of cells. So the pandas module basically allows us to work with data frames in Python in much the same way that we would work with data frames in R. So for those who came to the R lesson, we used the tidyverse group of packages to basically do a bunch of things to data frames, like filter out rows or select specific columns and do all those kinds of operations. All of that can be done in Python as well, using the pandas module. And so what we're going to do first, of course, we have to import the module that we want to use, which is pandas. And we do that in much the same way that we do for NumPy. So import pandas. And the convention in the Python community is to import this using the alias PD. In addition to the pandas module, we're going to import another module, which is called Seaborn. Seaborn as SNS. And we're going to use this package later on to do some data visualization. But we're also going to use it immediately to access a data set that we're going to use to analyze. Yeah.
But how, every time you import a package, is it a good practice to look in the internet? What is the convention?
No, I mean,
I don't know.
not you don't necessarily have to use this alias. You could use whatever alias you want. You don't have to use an alias at all if you just want to type out pandas in full every time, for example. But like the first time you use a package, you're probably going to Google how to load a data frame into R. And then you're going to come across Stack Overflow and the answer is going to say use pandas. And then it's going to be import pandas as PD. And then you're going to copy paste that into your code and you're never going to see or use anything else. So like the convention is kind of born out of people just figuring out on the fly how to do different things. And so like whenever I use pandas, I import it as PD because the first time I did it, that's just kind of how it happened.
But I would think it's a good practice maybe because everyone is going to know like PD is.
It will make your code more readable.
I totally agree. Like whenever you can, you should use whatever the convention is. And for these sets of modules, these are the typical aliases that are used. There's a host of modules that you'll use that don't have aliases at all. There's a bunch of them.
That's the majority.
Yeah.
These are the most common packages that you have.
So we could run that cell and it'll import both of those packages. It might take a second because they're rather large. But the first thing we're going to do is just basically create a data set. And we're going to do that using one of the built-in data sets from the Seaborn package. So we're going to assign the data set to an object called iris data. This is the iris data set on like flower shape that was collected by, I think, Ronald Fisher, like back in the 30s or something. Really famous data set for use in R and Python. It comes from the Seaborn package. So we imported Seaborn as SNS. So SNS dot load underscore data set. And the data set is iris. And so this is basically how we'll load that data set. And when you run that cell, we'll now have an object in our environment called iris data, and we'll look at it in a second. I just want to make you guys aware that, for example, if you had your own data set on your computer that you wanted to use and manipulate with pandas, pandas provides you the functionality to load that data in much the same way that R does. And the way that you would do that is data pd.read underscore table and then path to file. So the read underscore table function from the pandas library basically allows you to pass the path to your data set on your computer somewhere, and it'll just load that in. And this function has a bunch of arguments about like what the type of file is. Like, is it a CSV, a text file? Do you want to import the column names with it? Like, all of these different customizations are available as arguments to the read table function. But for now, we're just going to use the iris data set that's built in just to kind of get a sense of how we could start working with data in Python. So the first thing I want to do is just use the type function from Python on the iris data to just get a sense of what it is we're dealing with. If you ask Python what the type is for this data set, it returns this giant string here, pandas.core.frame.dataframe. So basically all of this is saying that this is an object or an instance of the data frame class from the pandas module. So because it's an instance of the data frame class, it means that there's a bunch of different methods and attributes that are associated with this object that we could then call directly using the dot notation that we've been using to access attributes and methods. So for example, well, first, actually, let's just look at what our data looks like in full. So we could do that by just, I guess I should print it maybe. If you print out the data, it's not going to print it in full. It only prints 100 lines or 150 by default, I think. But this is basically what it looks like. We have a bunch of different species of iris and then flower shape characteristics like sepal length, petal width, and those types of things. But often we don't want to necessarily print. I can't minimize that. That's okay. Often we don't want to visualize like the whole data set. Maybe we just want to see a part of it. So we could do that using a particular method that's associated with the pandas data frame class, .head. So this is similar to how you'd use the head function in R to just get, for example, the first few rows of a data frame. It is a method, so we do need the parentheses. You can just run it by default, but you could also pass an optional argument, which is n, to get a specified number of rows from head. So in this case, I'm asking it for 10 rows. And it'll just print out the first 10 rows of that data frame in order. So just put a little note here. But in addition to methods, what did you say the hotkey was on it to minimize the Shift O? No, no. Normally you just double click it, but so in addition to these methods, the data sets also have a series of attributes, right? Attributes are just storing data about that object. They're not performing any operation like methods are. They're just telling you something about it. So one of those for data frames is shape. And shape returns this tuple that specifies the number of rows and the number of columns. So it's giving you the shape of the data frame. In R, I think you could use the dim function for this, dimensions on a data frame, to return the same thing. But essentially it's telling us that we have 150 rows and 5 columns. And that kind of aligns with what we saw up here, 150 rows, 5 columns. So this is a class attribute. Just telling us some information about it. There are a bunch of other useful ones. So iris.columns. This is another attribute that will just basically return all of the columns in the data frame by name. And then it's just telling us that this is a data type object. It's an object because it's an instance of the data frame class, which is an object. I'm just going to write out some other useful methods and attributes. There's the info method, which basically just returns a bunch of information intuitively enough about this data frame. So for example, it's telling us that we have 150 entries. It's giving us all of these columns with the number of entries for each. It's telling us that most of that 4 of the columns are float objects. One of them is an object. I don't actually know what that means, but anyways, it's telling us a bunch of useful information that maybe you'd want to know. There's a more intuitive way to get this information. Yeah.
When you run this article that info without the parentheses, get different info, so like are there 2 different ones being called or?
No.
So I don't know why it's printing the actual data frame here. What this is telling you is that the info is actually a method that is bound to the data frame class. So when you type out a method, but you forget to put the parentheses showing that it's a method, Python will just be like, wait a second, this is a method. So it's not quite an error, but it's almost telling you like you're missing the parentheses here. This should be a method. There should be some arguments being supplied.
That's the same with functions as well. If you just try to print without the parentheses, it returns a bit of that garble as well, saying like this is a function.
Yeah, you could test that. Function print, right? So it's a function because it's not bound to any particular class, but because the info function is bound to a class, it's telling you that it's a bound method. Functions that are in classes are called methods. Functions that are not in classes are called functions.
Okay.
But they do the exact same thing. They just have different terminology.
I don't know what's pretty complicated. That's a weird bug.
Yeah, so it shouldn't print the data frame like this. I don't know if that's a Jupyter thing or a Pandas thing, but either way. Key types just gives you basically the type for each column. So is it an integer? Is it a float? Is it a string? Is it an object? I don't know why I think, yeah, I know, but I think by default, Pandas actually encodes what are strings as objects. So that's the default object type for strings in a Pandas data frame. I don't quite know why it does that, but I'm sure Pandas has its reasons. And then there's another, arguably maybe the most useful method that we'll see right now, which is .describe. And it basically just gives you a bunch of descriptive statistics for each of the columns in the data frame. At least each of the numerical columns. So all of the methods and attributes that we've seen operate sort of natively on the data set that we've loaded, but we'll often want to manipulate the data set in some way rather than just using it sort of in whatever shape or whatever manner that we loaded it in. And so to do this, Pandas offers a bunch of useful ways of selecting and filtering data. I'll just create a separate header here, block that off. So we could select columns using a list. So for example, you might load in a data frame that has a bunch of columns, but you don't actually need to use most of them for whatever analyses you're going to do. So you could actually create a separate object that's a list that contains the names of the object or of the columns that you want to keep. So in this case, remember, I'm creating a list as denoted by the square brackets here. And then the columns I want to keep are strings as elements in this list. And so if you want to pull these out of the data, all you need to do is index the data frame. And the way that you do that is using square brackets. So you use the name of the data frame followed by square brackets, and then you pass that list. And if I run this, as predicted, the output is only the 2 columns that we asked for. Now, importantly, I didn't modify the original data frame here, right? All I'm doing is telling it that I want these 2 columns from this data frame. If I wanted to, I could save this to a new object called like my subsetted data frame or something, and then it would just be a data frame with the reduced number of columns. But just by printing it out like this, I'm not actually modifying the data in any way. And it printed out the whole thing. I'm actually just gonna. So remember, because this is a data frame, data frames have methods associated with them, one of which is head, which we could use to just get the first 5 rows, 6 rows, 5 rows. Yeah.
What is it? How do I format my own?
What do you mean?
So, as I understand it, example data set, just a view.
Yeah.
And I wanted to use all of these. My text file.
Yeah. So you would have to use, you would have to load the data in, not using Seaborn, but using pandas. And so you would use something that looks like this. So you would use the read table function method from the pandas library. And then the only argument that you really have to pass to this function is the data frame on your computer. So the text file or the CSV file on your computer. And then it'll just load that in as the data. And then you could work with it in the exact same way.
So it would still understand the first line, column.
Absolutely. And you could customize that. You could pass as arguments to this function like header equals true, for example, in which case it expects the first row to be a header. You could tell it to skip some number of lines because maybe for whatever your reason, your header is like line 11. Like all of that is customizable. But yeah, you could totally just load in your own data and then do all of the same stuff with it. Changing the column names and stuff, of course. So we could also retrieve individual columns. And remember, when you start typing out iris, because it's an object that we have in our environment, you could hit tab and it'll autocomplete. This is really useful because we're going to be typing this a lot. So you don't want to have to type it out in full every time. So you could actually just do dot the name of the column, and you could actually just tab as well, and it'll autocomplete for the columns that are present in the data frame that match what you've written so far. So in this case, if we want sepal length, iris data dot sepal length will just return that column. And it returns that column as a separate object, which is known as a pandas series. And pandas series is a class that also has a bunch of different methods associated with them that allow you to do a ton of different things. So hopefully you guys are starting to get the sense that like everything in Python is an object that often returns another object that has like its own methods and attributes. But we're not going to talk much about pandas series in this case. But the individual values in a pandas column are called a series.
And they're based off NumPy, right?
Yeah. And so many of those functions in NumPy are translatable to the pandas series, and you can do vectorized operations on them and stuff. So that's for selecting columns, which is pretty standard. Sometimes you also want to filter rows. And in this case, we'll do it by index location. So for example, we have 150 rows in our data set, but maybe we actually only want rows 0, 5, and 10. Remember, row 0 is actually the first row in our data frame, right? We start counting at 0. And so Pandas data frames have a useful method called iloc, which stands for index location. And then it takes a list basically as its index, and it'll return that. The interesting thing to note here is that these are square brackets here and not circle brackets, right? So this isn't like a function to which we're passing arguments. This is actually like square indexing brackets to which we're passing the list containing the indices we want. So it's a bit of a weird function, but if for whatever method, but if for whatever reason you do want specific rows in your data frame, this is kind of how you would achieve that. Yeah.
Do you always have to do a list first? Or can you put like iloc and then the numbers?
I could have just done that, and it would do the exact same thing. The reason I didn't do that is because I find it a little more intuitive to actually just look at the list first and then pass it here rather than having to deal with like multiple sets of nested brackets. But you could totally just put the numbers in there yourself if you wanted to. So iloc is useful, and you'll probably see it come up quite a bit. Pandas relies on it more and more nowadays, whereas there used to be ways of doing this that didn't rely on ilocation. Similar to the NumPy arrays, you could actually just index the data frame directly. So for example, if you want the first 10 rows, you could actually just do iris data 0 to 10. Note, this is actually very similar to how you would index a data frame in base R, right? So if you weren't using dplyr and you wanted to subset a data set, this is kind of how you could do that in base R. One of the more useful ways to filter data is based on a Boolean. And what I mean by Boolean is true, false. So you specify some condition in your data frame that when it's true, will return those rows, but if it's false, it will not return those rows. So this is kind of like what the filter function in dplyr is doing in R. And so iris data, you could also filter sort of specific columns, right? So iris data, species. So now we're looking only at the species column. Equals Virginica. Probably isn't the most intuitive way to do that, but I just basically want to show you that if you look in the species column of the iris data and look to see if it's equal to Virginica, what it's doing is it's basically returning a pandas series of true and false. So if it's true, then that means the species for that row is Virginica, and if it's false, then it's some other species. So we could actually use this fact to subset our data set. And the way that we would do that is iris data. We subset it the same way that we did earlier by following that with a set of square brackets. And then we could actually just paste that right in. So we're subsetting the iris data based on all rows in this data frame where the species is equal to Virginica. And if we do that, we see that we only have rows 100 to 150, which are the rows where that condition matches. Does that make sense? You could also specify more complicated conditions. For example, maybe you want to filter by multiple conditions, right? You don't only want to filter by species. Let's say, for example, we want to filter this data set for all values of sepal length that are between 6 and 7. So greater than 6, but less than 7. So we could do that by specifying multiple conditions. The only weird syntax here is that each of the conditions has to be self-contained in a set of curly brackets, or not curly brackets, but just regular sort of circular parentheses. So iris data, let's say sepal length greater than 6, right? And we're going to specify our second condition in its own set of parentheses, iris data, sepal length less than 7. Just take a second to look at this. We have our data frame. We're indexing it with a set of square brackets, and then we're specifying multiple filtering conditions in each in their own set of parentheses spaced out by and. You could replace the and with or if you want to. You could replace it with exclusive or if you want to. There are a bunch of different sort of logical operators you could use to subset the data, but for now we'll use and.
What is it?
Exclusive or is like, it's like if you have multiple conditions, it's whether or not each of the conditions is included or excluded in the search criteria. I could show you an example. There's a way to do it in R as well. But I can't think of one to do on this particular data set. And so if you do that, looking at the sepal length column, you see that all of the values here are between 6 and 7. Perfect. Nice. So just, I think one or two more quick filtering things. Iris data. I'm going to write this out. I'm going to keep this consistent. Species is in. All right, so let me unpack this. So what I've done here is I've created a list of species that I want to retain. Like there's one way to do this would just be to basically filter our data frame where the species is either equal to Virginica or is equal to Setosa, right? Or another way to do this is to create a list containing the species we want and then use this particular method is in, which basically checks if the species in the species column of our data frame is in this list that we've created. And if you run this, you see that you only have rows with Setosa and Virginica. So like if you had a data frame with a factor in some column and you wanted to filter out the rows that only have particular levels of this factor, you could create a list with the levels that you care about and then use the is-in method, which is going to check each factor level in each row against that list. And then if it's true, if it's in that list, it'll return that row. If it's not in that list, then it'll exclude it. So you're only filtering for conditions where these are met. All right, last page. I'm going to create a markdown cell. So that's it for filtering and selecting columns. Does that make sense to everybody? And then finally, there's a set of really useful operations that you can do on Pandas data frames having to do with grouping. So iris data dot group by species. So what I've done here is I've created a separate object. I've created a separate object called species, where I've taken our original data frame And all I've done now is grouped it by species. What you'll notice is if you look at the species object, it's returning something totally different now, right? It's returning a data frame group by object. So this is different than the data frame object that we had earlier. What it's done is it's implicitly taken our data frame and it said, okay, these species are the first group, these species are the second group, these ones are the third group. And it did that based on the similarity in their names. So like all the Virginica are gonna be one group, all the Setosa are another. And then I don't remember what the third species is, but that would be the third group. And so it's just created this separate object type out of this group data frame. And this is cool because a group data frame has its own set of methods and attributes that we could use to get different characteristics about this data frame. So the first, for example, if we just ask what the length of this object is, it's going to return 3. And the reason is that because there are 3 species in our data frame. So when it grouped it, it resulted in a group data frame that's of length 3. So the length would be equal to the number of groups in the data frame. Group data frames have this cool first method. Basically what it does is it goes through the data frame and it returns the first row for each group, right? So it went through and it said Setosa, okay, that's the first group. What's the first row? It'll just return the whole row. And then it'll keep going. It doesn't return any of the additional Setosa rows, but then it sees versicolor. There's the next group, returns the first row. So this is really useful if, for example, you just want to see what the data looks like. Oh, coming back. If you just want to see what the data looks like at each location where the groups occur, just to get sort of just a first pass of what's happening in the data frame. Species, sepal length. And then it also allows us to use various methods that specify numerical operations on our data frame. So now what we've done, because this is a grouped data frame object, we could actually just ask, what's the mean in the sepal length column for each of these groups? If we were to do this on the original data frame, we could, but it would return the mean across the whole column, right? Because in the original data frame, it doesn't have any concept of this grouping. But now that we've grouped the data frame in this way, we could ask it for the mean for each of those groups and it'll give it to us. You could do similar things for maximum, minimum, median, quartile ranges, all of that stuff. We could also species. Group data frames have this particular method called getGroup. But let's unpack this for a second. We have our data frame, right? Group data frames have a particular method that is called getGroup. If you want, for example, only one particular group that's in this data frame, like the Setosa species, and then from that, we could use our describe method that we learned earlier to get a bunch of useful summary statistics that are specific to this group. And you could do the same thing for versicolor or Virginica. Notice like there are some parallels to be drawn here between this period that splits up the different functions and the pipe operator in dplyr, right? Each of these is returning an object that is kind of passed to the next one in the series, so on and so forth, ultimately giving you what you want at the end. And then finally, before we do like a minute or so of plotting, I'm not even going to bother. I'm going to go straight to plotting. I was just going to show you a way that you could sort your data frame by different values, but unnecessary. Yes, maybe. So I'm going to show you guys a couple of useful plots for maybe 5 minutes or so. Plots in Python are incredibly customizable, by the way, in much the same way that ggplot plots are. There's actually a ggplot module for Python that allows you to mimic the ggplot aesthetics in Python, because the R community is incessant like that and just like needs their ggplot. So they moved it over to Python. But the Seaborn package actually provides a lot of really pretty and nifty looking plots that we could access directly without much customization at all. So it's pretty cool. The first thing we're gonna have to do though is insert this cell. I'm just gonna type it out, matplotlib inline. So notice the % sign at the beginning here. This is what's called a magic command in a Jupyter notebook. This is specific to Jupyter notebooks. This isn't a Python thing. This is basically just making it so that the figures we're going to draw are going to render below the cells when we run them. If you didn't have this, you would actually have to call specific methods like plot.show to display the plot, and it's just kind of messier. So it's easier to just run this cell with the Jupyter magic, and then this way the plots will show up right below. Anytime you're plotting in a Jupyter notebook, it's easier to do matplotlib inline. That way your plots render immediately below them. So the first kind of plot is histogram. Since it's intuitive, and most of us have a general sense of what a histogram kind of looks like. So I want to plot a histogram of the sepal length column. It turns out that we could actually just use the .plot.hist function. Or I guess the hist function from the plot module. What is plot? Is it a module class?
I'm lost too.
I don't know what's going on here. Yeah, it is. So like this is our data frame subsetted. Data frames have a plot.
Sub-module of the data.
Yeah. And we could also specify the number of bins. You could customize, again, there's a bunch of arguments you could provide to customize it, but all we're gonna do right now is just customize the number of bins. And when you run that, the first thing it's gonna do is print out sort of what this is. This is the object type. It's telling you that it generated an axis subplot object that's part of the matplotlib library. We didn't load in matplotlib, but just know that it's loaded in when we loaded in Seaborn. And then this is what the histogram looks like. By default, not the prettiest histogram. But again, all of it can be customized. We'll see more and more pretty plots as I generate them here. We could also generate a scatter plot. So again, .plot. So this is the nice thing kind of about sort of NumPy, Pandas, Seaborn, Matplotlib, like all of these packages kind of build off one another. So like we're plotting using Matplotlib by specifying a method that's actually part of a Pandas data frame, right? So these modules are kind of talking to each other in some sense, which is what allows you to access methods in this way and do this kind of stuff. So by just specifying the plot method, we need to tell it what we want to plot. And we do that kind of like we would in ggplot, for example, in R. We specify the X and Y axes. And each of the arguments is separated by a comma. Whoa, width. And then because we're just using sort of the generic plot function, we have to tell it what kind of plot we're trying to generate. And you do that just by specifying it as a string. We're generating a scatter plot. This is what that default scatter plot looks like. So those are the default kinds of plots generated by Matplotlib. But we loaded the Seaborn package, and the Seaborn package is like a cool wrapper around Matplotlib that kind of makes the plots look prettier and allows you to generate more complicated plots with fewer lines of code. And so we could use some of those functions. So rel plot, do you know what that stands for, Ahmed?
I didn't want to create anything.
Maybe we could figure it out when we look at it. So notice the first argument is actually the data set here. Length.
Relational plots.
Relational plot. So scatter plot,
Yeah.
basically. So if you wanted to, you could, this is basically using the Seaborn package to generate a scatter plot. That's basically the same as the one that we generated up here during using matplotlib. One advantage though, is that if you copy paste this into a different code cell, you could provide this additional argument that's hue and specify the column in your data frame that you want to color these points by. And when you print that out, it will just color it for you. This is equivalent to like providing the color argument in the aesthetics to your ggplot function in R. I'm just going to show two more quick plots. First is a pair plot. What? Yep. So this is a super sweet plot that I really like. So basically what it's doing is it's kind of like a facet grid thing in ggplot, right? So for every column in the data frame, it plots it against every column in the data frame and then colors the points by species. And like, we did this with one line of code. So this is super useful if you want to like, if you have a matrix and you want to visualize like pairwise correlations between them or something, like a bunch of traits that you measured on plants or animals or whatever, like this is a useful way of just like, in a quick and dirty manner, kind of seeing what the relationships among all your different variables look like, colored by different factors if you want to. And it even shows like cool histograms for each of them. Really useful. Love it. Love it. And then the last plot I'll show is what's called a joint plot, which is, I kind of added it at the last minute. I've never generated one for any reason before, but I think it looks cool and might be helpful. For some reason, I haven't quite figured out why yet. The order to the arguments in this function are a little bit different. In that it wants the data last. Oh. So the joint plot, what it's doing is it's plotting it's giving you a scatter plot. It's also putting the best fit linear line from like a linear model of those two variables against one another. And then it's plotting a histogram showing the distribution of each of those variables on top of the plot. That's pretty useful. So like for these types of complicated plots, yeah. For these types of complicated plots, like the Seaborn package provides a lot of useful ways to generate like quick and dirty visualizations. These types of plots would actually be, I think, more difficult to do in R, to be honest. Like if you wanted to generate this kind of figure in ggplot, it would be more challenging. But you could do it with one line of code in Seaborn. And then again, you could, using Seaborn and matplotlib, you could customize everything about the axes and the size of the plot and the color of the points and the lines. All of that is customizable using methods and attributes in the same way that we've been using them on the data frames and the NumPy objects. So because each of these returns an object, those objects have attributes and methods that allow you to modify those objects, either in place or generate new ones. And because of that, you like have endless customizations available in terms of like how your figures look and stuff. This is just to show you sort of a snapshot of the diversity of the types of figures that you could generate. But again, everything is fully customizable. and you can basically do whatever you want with your data.
So do you have to put each of the elements in an order? Like, you just said like data goes at the end. I was wondering if
Yeah, so it largely depends on the method and how it's written. So like some methods and functions will expect the arguments to be passed in a particular order. In Python, there are ways of specifying that the order doesn't necessarily matter. There are ways of making some things optional. For whatever reason, I'll try it, but when I put, my intuition was to have data here, but yeah.
What happens if you specify X and Y as named arguments?
That's true.
Doesn't it have like default orders if you just specify arguments positionally?
So that's fine, yeah.
Okay.
So it just didn't know what the next arguments were, which is why it threw the error.
How do you copy those graphs? Is there an easy way?
Yeah, there
How would
is.
you put that into the document then?
Well, actually, the beautiful thing about Jupyter Notebook is that what you do is you just go to File, Save as PDF.
Oh, right.
And then it does it. But there is, there's like a sns.plot.save or something. Like if you want to just save one particular plot to like a PDF on your computer, a JPEG or whatever, the Seaborn package has a function that allows you to do that. If you want the whole notebook, then you just compile the whole thing to PDF. Yeah.
If you just go like irisdata.plot, and it kind of generates like this big thing, and I'm like, what's it doing?
Oh yeah, let's give it a shot. So iris dot plot.
Dot plot with friends.
Whoa.
Yeah.
So the default plot is trash.
You've got the index on the X.
So it's a line plot with, but what's on the Y?
Whatever value there is for each of those.
Yeah, so your
like a times
your X is like the position in the column.
Yeah, in the data
The
frame.
data frame.
Yeah.
That's
And
horrendous.
It's just like the value associated. with
Yeah.
the Y.
There we go. So basically, by default, plot will look at your data and try to plot everything in as convenient a way as possible. And you know what? It did a decent job, right?
I mean, the code is
Consider all the
nice.
columns.
You could see the differences. It did. So I guess what it isn't doing is it's not encoding anything about species, is it?
No.
no, but you can see
But
Those
when the
are
random jumps happen,
like every 50 rows you have different.
But the trend
Yeah.
is supposed to.
Yeah, that's true.
The order.
Well, we
of
know
these-
it because.
Yeah.
of the-
But I guess that only occurs because the species are ordered in the data frame.
Yeah.
If they were unordered, it would be a mess. So it's really plotting the data frame like as it is.
I think that's useful for time series analysis, where you have temperature precipitation. Then you have like order by day, and then
Whoa.
And so if you do the same thing on our grouped data frame by species, what it's going to do is it's actually going to generate a separate one of those for each species. Which is intuitive because the group data frame is split by species. So it creates a split plot essentially.
If you were to do a time series, I would just do the more explicit plot and specify kind of line pattern, because this seems a little unpredictable. But that's just-
That's it, y'all. Thanks for coming out. Hopefully that was useful.
Cool, but yeah, I mean, all of this is basically just a snippet of what all three of these packages do. There's so much out there, but fortunately, all of it is documented. So if there's something you want to do, there's a ton of